Good morning, ladies and gentlemen. My name is Gaetano Zizzo. I am a professor of power system at the engineering department of the University of Palermo. Today, I will present a lecture titled Energy Storage Systems Integration in Electrical Power Systems, Regulation, Dimensioning of Integrated Systems, and Use Cases. For me, it's a great pleasure to give this lecture on this topic, since I've been working on battery storage systems from, since I think 2010. So it's about 50 years that I work on this topic, and I've been part also of the IEEE group devoted to the writing, to the preparation of the first of the first white paper on storage systems. So it's a topic that on which I usually work with my PhD students, and I hope that you will find interesting at this presentation. Let's start with a brief introduction for starting the understanding why battery in general energy storage systems are so important for electric power systems today. As you know, all the electrical power system in the last decades has faced a very great transformation that is due to the introduction of new generation plants, photovoltaic systems, wind plants, and so on, and to the introduction of new loads, for example, electric vehicles, but also a lot of electronic-based loads, and to the introduction of power electronics. In the last 20, 30 years, renewables, electric vehicles, and power electronics have become the new important challenges for the electrical power systems worldwide. And they are causing a shift of the power system towards a sustainable and renewable-based energy systems. This has fundamentally changed the conventional power grid operation, the conventional power grid management, and has introduced new problems, new complexities that the traditional infrastructure was not ready to face, was not designed to address. As an example, the spreading of distributed generation, so the spreading of new generation units connected to the medium voltage and the low voltage grid has caused a lot of problems, in particular in primary cabin at the section where at the node where we have HV and V transformers, because in some areas we have reverse power flow. So we have an active power flow from the distribution to the transmission grid. This is a new situation that, for example, our protection devices were not ready to face. And in many cases, and Italy has various examples of these cases, the connection of new renewables units have been limited by the distribution system operators worldwide because the protection of the grid were not ready for reverse power flow situations. This is only an example, but the first and the most important thing is that due to the increase of renewable, due to the increase of new loads, like, for example, electric vehicle, the historical paradigm of grid management for matching perfectly generation and demands have become increasingly inadequate. Because we have introduced in the power system new unpredictable sources, new unpredictable resources. Wind plants are, for example, one of the most unpredictable resources that on which that we have to compensate. And for compensating the rapid fluctuation in generation, we need systems that are able to give quick response, that have high efficiency, and these systems are, for example, energy storage systems. Energy storage systems can be used to store the excess power from the unpredictable generation and to supply the shortfall in generation for maintaining both the grid frequency, that the most important feature of the grid, because without a stable grid frequency, we have an unstable grid, we have system split, we have blackouts and so on, but also energy storage systems can be used for restoring voltages, for maintaining the voltage in the different nodes of the grid in the ranges that are allowed by the distribution system operator or transmission system operators. What are the advantages of storage systems? In particular, my lecture will focus on electrochemical storage systems. And electrochemical storage systems have three main advantages with respect to other conventional solutions for storage, for example, hydro pump storage, flywheels, or compressed air energy storage. The three main advantages are listed below, and they are high modularity. The high modularity of electrochemical storage systems guarantees ease of installation and flexibility of use. So we can install a given unit of storage in a node of the grid, and then if we want to increase the amount of storage in that node, we have only to buy another unit compatible with the first one that can be managed by the same battery management system at that node. And this is a great simplification for installing a regulation device. The second advantage is the very short implementation time. This is a fundamental characteristics, in particular, if we compare the electrochemical storage with other storage solutions, for example, with the hydro pump storage. In a few time, we are able to install a battery storage system in every node of the grid. We need a very small place for locating the storage, few tens of square meters, and we usually found commercial solutions with voltage source converter units in their cabin and batteries in their cabin that must be only transported to the place where they have been installed, and they only must be connected between each other and to the grid. So it's very easy to install and to implement in a short time a battery and electrochemical battery systems. Finally, we have the possibility of distribute in various locations of the grid various electrochemical electric storage systems. So we don't need a unique hydro pump storage in a place. We can install different units in various points of the grid, and in this way we can provide to the electrical system different services. We can install the right system for the existing infrastructure, so without modifying the section of the lines, for example, or the rating of the transformers present in a given section of the grid, because we can choose the right solution for that node. Talking about electrical energy storage systems, we must know exactly what they are. For electrical energy storage system, we intend a set of devices, equipment, and management and control logic functional for absorbing and releasing electricity and planned to operate continuously in parallel with the distribution or transmission grid, or capable of involving an alteration of the exchange profile with the grid itself, input or withdrawal, even if determined by voluntary disconnection, reconnection of part of all of the plant. This is a definition that is taken from an Italian technical standard that is a mandatory standard for connecting active users to the grid. And the battery storage system, in general, electric energy storage systems are considered as active users, so as users that can inject power into the grid. So they are considered as generators, and they must respect the same technical rules for connecting generators. Based on this definition, an uninterruptible power supply is not considered a generator, since it is based on batteries that can only take energy from the grid and inject the power towards the load. All other solutions comprising also bidirectional converters that are not considered UPS are instead considered as generators. And this definition comprises two kinds of electric energy storage system. Electrical energy storage system in which the accumulator are exclusively batteries or secondary electrochemical cells, and electrical energy storage systems in which the accumulators are exclusively capacitors or supercapacitors. So, supercapacitors and batteries are both electricity storage devices, but they differ significantly in how they store and release energy. Supercapacitors are able to deliver high power quickly in short bursts and have a longer lifespan with respect to batteries. Batteries, on the contrary, have higher energy density, are able to store more energy for longer periods, but typically they have a shorter lifespan and slower charge and discharge rates. This figure on the left of the slide synthesizes for some of the possible electricity storage systems the relation between power density and energy density. As you can see in the figure, capacitors belong to the left part of the graph, so they have lower energy density. You see in this figure usually lower than 5-6 watt hours for kilograms, but they have a very high power density that is usually comprised between 50 and over 10,000 watts for kilograms. So they are perfect for delivering services, for example, related to frequency regulation, or better, to virtual inertia, a service that I will show you later. On the contrary, if we examine the graph, we can see that the energy density of the batteries that are represented in this case are usually, energy density is usually over 2 watt-hours for kilograms, and can reach for lithium-ion battery also 200, 300 watt-hours for kilograms, but the power density usually is not over 1000 watts for kilograms. So different characteristics and different applications, and so for each specific application of storage system connected to the grid, we will have to choose the right technology able to deliver a given service. This was only a short introduction, and now we will not go into the detail of technologies, but we will only focus on grid integration service, on some characteristics of the batteries that must be provided by manufacturers for giving these services, and we will give indication about the sizing of these systems. If you have questions about this seminar, about this lecture, you can write your question in the chat of the Teams room, or you can make your question at the end of the lecture, and I'll try to answer to everyone. So let's start introducing grid or ancillary services. What are these services? Well, in order to avoid degradation in the quality of service, and in order to ensure both security and safety of the electrical power system under all operating conditions of the grid, so both under normal conditions, but also under abnormal conditions like faults, like overloading, etc., battery energy storage systems can be required to provide some services named ancillary services that are the ones listed in this slide. The services normally are related to the control of the or to the regulation of frequency and voltage. But they are also related to the capacity of maintain the battery storage system in service also during a fault, or to use the same battery for creating a new grid after a blackout. So the services in which battery storage systems are usually adopted are energy arbitrage, peak shaving, congestion management, load following, voltage regulation, voltage support during short circuits, fault ride-through capability, frequency regulation, virtual or synthetic inertia, and black start capability. Now, we will introduce one by one these services for making more clear how for each service a storage system can be used, what it can provide to the grid, and so on. But it's important to underline a point. Who is the owner of the battery storage system for providing such services? Well, the question is not unique. It depends on the country. It depends on the specific situation. It depends on the fact that the storage can be used in a pilot project or not. But in general, when we talk about grid services, we are in a situation where grid services can be provided both by storage systems belonging to DSOs or TSOs and by energy storage systems belonging to private users. So it depends by situation by situation. What is important to understand, moreover, is which kind of service can be requested from a storage system connected to the transmission grid or to the distribution grid. So we can distinguish storage system between among grid-scale battery storage and the local storage systems. To the first category belong all storage systems connected to the transmission level. So in general, these systems have a power that exceeds 10 megawatts or more. And they can have a discharging time of between 30 minutes and 4 hours. And this kind of storage systems at the transmission level are installed for enhancing the overall grid stability and efficiency through advanced monitoring and control capabilities. So they are very important for stability, for the security of the grid, for increasing system resilience. Local storage systems, instead, are connected to the distribution grid. So they can be connected behind the meter, for example. They can belong to private users, and they can be connected both to the low voltage and medium voltage grid. And in general, they are used for improving grid reliability and power quality for end users. They provide voltage support, power quality enhancement, and load management functions. All these capabilities enable robust backup powers, simple renewable integration, and efficient demand response, and ensure stable and reliable power distribution to end users. The question is, what are the technical rules to which these systems must be compliant? Well, technical rules for the connection of storage system to the transmission and distribution grids are established country by country by local TSO and DSOs. Even if often they are based on the indication from international entities, like for example in Europe, indication by ENSO-E and EDSO. Usually these indications are quite general in order to let each TSO able to introduce specific rules for the need of each country. Each country has different mix of has a different energy mix, has different problems in grid management, and so each TSO or DSO is able to introduce its particular indication for connecting batteries to the grid. A unique regulatory framework for storage is still missing in Europe. Here you can see, for example, a table that is taken from EDSO for smart grids integrating electricity storage in distribution grids, a document that is has been edited, has been issued in 2016, and that gives indication on which service, what services storage systems connected to distribution level should provide. These services are generation adjustment for solving congestions in grids or so in lines and transformers, active and reactive power provision for voltage control, and peak shifting and peak shaving for increasing the efficiency and for increasing the the life of the components of the grid. Anyway, both if the system is if in the case that the storage system is connected to the transmission grid, and in the case is connected to the distribution grid, one important thing is that proper hierarchical coordination of all the battery storage system in the grid is implemented. Usually, the hierarchical coordination of batteries presents three control layers. A primary control that is devoted to manage the individual device, the individual storage performance, through a direct control of the battery systems, and that includes state monitoring, thermal management, and real-time response to optimal operating conditions. This is the primary control. It only focuses on the single unit. The secondary control ensures the grid stability and the power quality through regulation of key electrical parameters, including frequency, voltage, and power factor to maintain reliable grid operation. So the secondary control is the one, for example, that coordinates all the battery units in the system for frequency regulation, for voltage regulation, and avoiding grid congestion, and so on. Finally, the tertiary control focuses on a system-wide optimization and economic operation through the participation to the electricity market, through load prediction, and through resource allocation strategies that maximizes efficiency and minimizes operational costs. So the problem is that we don't have only to manage the system in a secure and safe way, but we have also try to do this in an economical and optimized way, because we have to reduce the management and installation costs of the units if we want that storage systems can become in time a very spread solution for grid management. In this figure, you see also another view of the control system. We have the energy management center, and in this figure you see not the three control layers, but three functions that the energy management system of batteries of the distributed storage systems must implement for a reliable implementation of the service. So we must implement a system protection. So we have to monitor currents, we have to monitor temperature, voltages, and so on. We must implement monitoring and control, and then we must control the voltage source converters coupled with storage systems in order to provide active and reactive power for grid services. Now we can focus on each grid service that storage systems can provide to the grid. The first one is energy arbitrage. Well, what is this service? All storage systems perform a function that is a the time shift of energy. Indeed, they can be used to absorb energy in a period and release energy in a different period. And so, starting from this consideration, we can use a storage system for absorbing energy when we have a low price or that in general correspond to a low demand period, and then to release the same amount of energy, almost if we consider the charging and discharging efficiency. So release this same amount of energy in a different period where we have an high price for electricity and a high demand. So we can buy energy at times when the prices are low, and then store energy in the storage system and resell the energy at times when prices are high. In this way, we can have, considering also energy losses in the system, a revenue from selling this energy. The economic advantage is obviously determined by the difference between the purchase and resale prices at the two different times. Well, this function, we can imagine this function as a function that is provided by a private user that wants to have a revenue by purchasing and selling again electricity. And so usually formulated in this way, this service is more a market service that can be done from end users. But if we focus not only on the economical aspect of this service, but also on the stability issue, we can understand that this function can be useful for the whole power system because thanks to energy arbitrage, we can avoid, for example, the cutting of generation from renewables in periods when generation exceeds load. Let's imagine a situation of an isolated system. In Italy, we have a lot of small islands, very small islands, with only diesel or oil power plants, which rated power is not over, in general, 10, 20 megawatts. They are not connected to the main transmission grids, and sometimes the use of photovoltaic systems is not possible in these situations because especially during the hours around midday, we don't have an adequate load for absorbing power from photovoltaic system, and so we can use storage for this purpose. We can store energy and release it later. The sizing of the batteries for this service depends both on depends on a technical and economical analysis. So the user that want to install a system for energy arbitrage must be aware of the market prices, must be aware of the load profiles, in the area, in the market area, and so must study the market results of the previous years, and then must evaluate the right size of storage to install for delivering this service with an adequate payback time. Usually for this application, a payback time of 7 years is acceptable. Over 7 years is not considered convenient. The second application is peak shaving. Well, in this case, batteries make it possible to mitigate consumption peaks by storing energy during periods of low demand or high production from renewables, when generation plants are forced to operate in less efficient settings. And then storage systems are used for releasing the stored energy during periods of higher demand. In this way, avoiding the use of peak plants that have lower reliability and higher variable costs. So it seems similar to energy arbitrage, but the aim of this service is totally different. In this case, we don't have a private user that wants to buy and then sell again electricity to the market. We have a service that is provided to the grid for making the grid more efficient, for reducing evening power ramps of the of thermal power plants, to, for example, to the reduction, to the quick reduction of the power provided by photovoltaic systems, and for reducing the general cost, general operating cost, or general production cost of a given power system. On the right, you see a very famous figure. You see the famous duck curve that represents how the load during around midday is reduced due to the implementation of new photovoltaic plants. So the load that then the remaining load that is seen from thermal power plant is reduced. So we have between 10 and 17 a very important reduction of the load, and we have thermal power plants that are working at very disadvantageous conditions, and then suddenly after 17 we have this increase in the load seen by thermal power plants. We need to use peak plants, and this can create important problems to the power system. Thanks to the storage, we can cut this part of the load, so we can increase the load during these hours, and then we can decrease the generation, the use of peak plants during these evening hours. And this, believe me, gives a great advantages to the TSO. So these systems should be used by system operators, but they can be used for this purpose also by private users that can provide the service to the TSO. Third service is congestion management. Well, congestions are becoming more and more frequent in our grids, both at distribution and transmission level. Well, this depends on the fact that load and generation is increasing faster than the time that DSO or TSO need to strengthening their networks. And so in some cases, we can have a situation where lines are can carry more than their rated power, their transport capacity. This can create instability, this can create overloading, and this can create the detachment of the line. And this is a situation that must be avoided. So in the figure, you can see how storage systems can be used for avoiding a congestion in the line, the second line, the one with the lightning, where without storage, the line would carry 130 megawatts of powers. Well, this 130 megawatts could be higher than the capacity of the line. So using this storage unit, we can store 30 megawatts. The line carry only 100 megawatts that are lower than its rated power. And the second storage that has stored 30 megawatts before can provide the same, can give to the grid the same amount of energy that was stored in the first unit. In this way, we have a flow from the wind plant to this unit and a flow of energy from this unit to the user. And this line is working in a more in a less stressing condition, and the market balance is still respected. Another possible use of storage system for congestion management is using only one unit, for example, the first one, that store energy in a given hour when we have an excess of production from the wind plant, and release then the same energy in a later time interval when the production from the wind plant is reduced. In this way, both in the first time interval and in the second time interval, we have the line, the line here, that is carrying an adequate power and is not suffering overloads. Other service load following. If we study the daily load profile, we see that we need a base load capacity, a load following capacity, and a peaking loading capacity. So we need power plants able to produce an almost constant power during the whole day. We need power plants that are able to modify their production in very quickly, in few minutes, for following the load. And then we need power plants that are used only for providing power in extreme situations, for compensating peaks of loads. Well, if we give a look to this figure on the left, we can see that load following power plants are usually able to modify their power in times that are comprised between 0.2 minutes in the case of diesel or gas engine, and 45 minutes in the case of combined heat and power. Storage systems instead can provide the same service, varying their power output very quickly in a few seconds, and so can be used as load following units in different situations. In this way, providing the same services faster and with less stress for the thermal power plants. Well, this is one of the most important services that can be provided by batteries in a power system. Voltage regulation is a service that we need both at distribution and transmission levels. We know that voltage values in distribution and transmission networks must be kept within plus minus 10% of the rated voltage. If we go outside this range, maximum and minimum voltage protection usually are triggered. And moreover, we can have problems to the load or to the grid. An excessive voltage increase can cause increased losses in the cross elements of lines and transformers, can cause saturation of transformer cores, excessive stress of insulation of cables, for example, increased corona phenomena with increased losses, and increase the probability of air discharge, in particular for over the lines. While an excessive voltage reduction can cause reduced line carrying capacity and stability margins. This is a very important, very dangerous situation for transmission lines that can cause system splits, for example, can cause increased currents and thus an increase also in losses for Joule effect, reduced reactive power capacity delivery by shunt capacitors that need an adequate voltage for delivering their function in a proper way, and problems with starting or using some electrical loads, in particular some loads based on electronics. So our objective is to maintain voltage between 90% and 110% of the rated voltage of the system. We know that the voltage drop or the voltage increase in case of distributed generation on an impedance consists of a part depending on the active power and on the reactance, on the resistance of the line, and on a part depending on the reactance, inductive reactance of the line and on the reactive power. And so we can use this expression on the left for calculating the voltage drop or the voltage increase in a line. In distribution networks, we have resistance and reactance that are in the same order in case of medium voltage line, or we have resistance that prevails over inductive reactance in low voltage lines. While in transmission networks, usually the resistance of a line is negligible with respect to the reactance. So in transmission networks, we say that the voltage variation in a node of the grid depends only on the reactance seen by that node, so above that node, and on the variation of the reactive power injected in that node. So if we have an higher request of inductive reactive power in a node of the grid, the voltage of that node decreases. If we have an increased request of capacitive reactive power in the same node, the voltage of the node increases. And so, for compensating this voltage variation, we need to use some devices able to provide in transmission grids reactive power, while in distribution grids we can regulate the voltage in a node, both varying the active power and the reactive power. Well, regarding this last aspect, when we vary reactive power, we usually do it for voltage regulation, but active power is usually managed in a given node for frequency regulation. Anyway, in many cases, in distribution grids, the variation of active power is necessary for having a better regulation of the voltage in a node more than the variation of the reactive power. So we can use battery also for this service. So the devices involved in voltage regulation are usually a generator that are rotating or static, transformers and autotransformers, power factor correction capacitors and cross compensation reactors, rotating compensators, static compensators, the so-called FECs, users, semi-users of the system that are required to keep their power factor within an appropriate range, usually between 0.95 and minus 0.95, and then electrical energy storage systems. In reality, this last point can be included both in the case of FECs and in the case of generators, since if we remember the definition of storage systems given by the Italian technical rules, they are systems that are considered of the same kind of power generators. And focusing on batteries, this is the case of batteries with its of a battery with its inverter that can inject a given active or reactive power into the grid, or can absorb can absorb from the grid an active or reactive power. And varying these quantities, the storage system can regulate the voltage at this node. We have in this case an interface protection device that is sensible to the values of the frequency and voltage at the point of common coupling between the storage system and the grid, and is usually set between 90% and 110% of the rated voltage of that system. And you see on the right an example of capability PQ capability curve of the storage system coupled with its inverter. The inverter has a rated power indicated by Sn. The storage system has a maximum discharge power indicated by PS max, and the maximum charging power indicated by PC max. So some regulations requires that the inverter coupled to the battery storage system can be controlled in order to provide all the couples of active and reactive powers included between the circle and the dotted line representing the maximum charging and discharged power. So this inverter for regulating the voltage in the point to which it is connected must provide both PS max and must absorb PC max, and at the same time should be able to provide both minus Sn of reactive power and plus Sn, or any combination in this area. Well, how can we choose the sizing of such a system for this kind of service? It's quite easy, because for choosing the size, we must consider that the system, the inverter must be able to modify the voltage between 90% and 110%. So we must know the equivalent reactance, at at the point of common coupling, the equivalent resistance of the point of common coupling, and starting from these two parameters and from the value of the rated voltage, we can calculate the maximum variation in reactive power and the maximum variation in active power in that node, for maintaining the voltage of the node between 90% and 110%. So the regulation is only local in this case. Other important service that the storage system must be able to provide is the fault write-through capability. So if we are using a battery for providing grid services, for example, for balancing active power or reactive power, it is important that during a short circuit in the grid, the battery remains connected to the grid, even if the voltage at the point of common coupling exceeds some higher values or goes below some very low values. This is important because the service that the batteries must provide must be delivered also after the elimination of the short circuit. So if we consider that during a short circuit, a large amount of reactive power is injected into the grid towards the fault location, you understand that this large quantity of reactive power can determine in the grid a very high voltage drop. So we can have during the fault voltage reduction that in this figure you see can reach also almost 5% of the rated power, or higher values. Here we have 85%, for example. But after the fault has been cleared by the system protection, well, in that case, we can have some return over voltages, and so temporary, the voltage at the point of common coupling between the storage and the grid can exceed the 10% established by normal operation conditions. So we can reach also 150%, 130%, and so on. So we have the interface protection relays connected to the storage that detach this storage system when the voltage is too low or too high. Well, in this case, if we want that the storage system remains connected to the grid also during the fault or after the fault, during the voltage transient that is established after the fault clearance, we need to implement this curve in the in the protection system of the inverter coupled to the storage system. You see that the fault rate 2 characteristics in this case include the possibility of maintain the storage system connected to the grid, even if the voltage at the point of common coupling goes below the 85% of the rated power or goes above 150% of the rated power. In this case, the storage system must be maintained connected for an infinite time to the grid. But if the voltage at the point of common coupling goes below 5% of the rated power, the battery must be able to stay connected for no more than 200 milliseconds. Then this time is increased with the increase of the voltage measured at the point of common coupling. This line, this gray line that I'm underlining in this moment, represents the low voltage right to characteristics that separates the detachment zone of the storage system from the operation zone. Now see the upper part of this figure. We see that the voltage that the storage system can tolerate when we have a return over voltage after the clearance of the fault can reach 125% of the rated power. In this case, this voltage can be tolerated for 100 milliseconds. Then, if the over voltage is longer than this time, the over voltage that can be tolerated is reduced, and then we reach the maintenance value, the allowed value of 115%. This line, this gray line, represent the over voltage right to characteristic that the storage system must provide, must have for stay connected during the return over voltage period, the transient that we have after the clearance of the fault. It's very important. It's very important because we can't lose regulating resource every time we have a fault in a grid. If we have a fault in a grid, usually we need, after the fault, that the regulating resources, storage comprised, can intervene after the fault for restoring the previous operating condition, or stable operating conditions for the rest of the time. So this characteristic is important for maintaining regulating resources. And this is a future step in the service that storage system can provide to the grid, because we have here another important function that must be implemented by storage systems during the fault. So it's important not only that the storage system stay connected to the grid during the fault or during the transient that will occur later, but in some cases the same storage system must help the grid supporting the voltage in the point where it is connected. So if we have a reduction of the voltage in the point of common coupling that is over 15%, here. So the voltage during the fault is reduced more than 15%, and from 15% to 50%, the battery must be controlled in order to inject into the grid capacitive reactive power with this slope. This capacity reactive power, so when the voltage has been reduced to 50%, the current, the reactive current injected by the storage system must be equal to the rated current. This function allows the storage system to contrast the voltage reduction. If the storage system contrasts the voltage reduction, it can be used for helping all the other generators in the same area, close to the node to which it is connected. So in this case, the storage system is used for supporting voltage in an area of the grid, helping to maintain the connection of the other devices closer to that node. On the contrary, if the voltage in that node increases over 10% of the 110% of the rated voltage, in this case, the storage system is controlled for increasing the absorption of inductive reactive power. In this way, it behaves like a reactor connected to that node and helping in reducing the voltage of the node. Reducing the voltage of the node and bringing the value among the normal operating values, normal operating ranges, all the generators close to that node can stay connected without triggering of their interface protection relay. So, stay connected during the fault and helping the grid during the fault. Two functions that batteries can provide easily because they have a very quick response to a control signal coming from the grid or to a control signal that is activated by the same measuring systems on board of the battery storage systems that can measure locally frequency and, in this case, voltages. The second very important service that the storage system can provide, and that is close to voltage regulation, is frequency regulation. Voltage regulation and frequency regulation are the main services that must be always ensured in a grid. Frequency is like the heartbeat of our body. The frequency must be maintained always in a specific, very limited range if we want that the system can be operated in secure conditions. And frequency regulation is used for maintaining stability during disturbance, for improving transient stabilities. What is transient stability of a power system? Is the property of an electrical system to maintain synchronism when subjected to severe transient disturbances, such as those arising from a short circuit, loss of a power plant, or loss of a large portion of load. for making you understand what is a large disturbance. For example, the Europe, most of the countries of Europe are included in a single synchronous area that operate like a very large transmission grid and very large unique grid on almost on the whole Europe. That is the continental Europe synchronous area. And for the continental Europe synchronous area, we have a reference incident that is 3000 megawatts. So the primary regulation in our continental Europe area is done and is designed, is sized for contrasting a disturbance up to 300 megas. So if we lost 300 megawatts of 3000 megawatts of generation, 3 gigawatts of generation, the grid is still stable and a blackout can't occur. Well, in what phase of frequency regulation the storage system can be used? This is only a brief reminder that we have primary, secondary, and tertiary regulation, because during a fault, for example, during the loss of generation, frequency decreases rapidly, only contrasted by the governor response and by the inertia of the system. The governor response in this case is activated immediately, and in a first phase that is usually of 30 seconds, the regulation system, the control system of the power plant must contrast the reduction of the frequency. So after 30 seconds, the frequency reduction is contrasted, and the new value of frequency, that is no more the rated one, is reached. So we are still working, but no more with the rated frequency. Then we have the secondary frequency regulation, that is the one that reports, that adjusts the value of the frequency and bring it to the rated value. And then the tertiary frequency regulation, that where the generator are dispatched by the centralized control in order to restore the balancing resource of the system. Well, storage systems can be used in all three stages of frequency regulations. Anyway, we will focus in this case only on the first part of the frequency regulation, only on primary frequency regulation. These are some definitions taken from ENSO-E documents. These are some values from ENSO-E, and let's refer to this scheme. Here we can see the classical representation of a single area system, where we can distinguish the regulating action of power plants during a power disturbance, an active power disturbance, that is this one, delta PD, and this represents the action of thermal power plants, hydropower plants participating in the primary frequency regulation. The effect, the power plants participate considering their the maximum power they can deliver, their active droop, and with this formula that represents the power energy characteristics of the power plants. This other block instead represents the natural response, the natural response of the power system to a disturbance is a response depending on the regulating action of the load itself, that during the year is becoming more and more weak due to the new diffusion, to the spread of power electronic based load that have no more this intrinsic response to power disturbances, and depends on through this constant on the system inertia. These are the formulas for calculating system inertia, the system inertia and the inertia of the single generator. At the end of the disturbance in the power system, we have a frequency variation, maximum frequency variation, that depends on the rate between the disturbance and the sum of the power frequency characteristic of the load and of the generator. Well, this is what happens without the contribution of storage systems. So in this case, after the disturbance, we have a frequency variation, and what contrasts frequency variation is this quantity, ER. But the action of the generator is as lower as higher is this time constant TR. That is the time constant depending on the intrinsic characteristic of the thermal of the power plant. If we want to increase system stability, if we want to reduce the maximum steady state frequency variation after the disturbance, we can use storage system for providing their contribution to frequency regulation. In this case, the storage system is connected to a voltage source converter, and its transfer function is represented by this triangle K group. The transfer function, so it's simply a constant. We don't have a delay, because if compared to the intervention time of the turbine governors of classical power plants, the intervention time of a battery storage system is so small that usually it is neglected in this kind of representation. We are talking of a few hundreds of milliseconds, at maximum 1 second. So we can have the same action of the same regulating action of a thermal power plant, of a hydropower plant participating in frequency regulation, with a very high response time. For this reason, we talk of fast frequency regulation when we use storage systems for providing such a service. And how can we size a battery for this kind of service? Well, it's not so simple, because it depends on the number of batteries that we will use. We can start sizing choosing the maximum power of all the batteries that are connected to that area for providing that service. So we can calculate Pmax, that is the sum of all the rated power of all the batteries that provide the service, in this way. We can establish what is the maximum frequency deviation in steady state that we want to obtain at the end of the disturbance, and thanks to this formula, this one, if we include in this denominator plus K droop, and we impose the maximum city state frequency deviation, we can find the K droop to be implemented. And from this formula, having set the dead band and the saturation band identify the frequency saturation band identify the maximum value of the frequency after which the power from the storage is equal to the maximum allowed, we can calculate Pmax. Then, for calculating the energy that must be stored into the storage system, we can multiply Pmax from the discharging efficiency of the batteries, and for the number of times in which the service must be delivered, so the number of discharge operations imposed to that system, and then we can impose the time, the discharge time that depending of the local regulation can be between 30 seconds and 15 minutes. Since we are sizing the system only for participating in primary frequency regulation. Then, in this way, we have found the total power that must be installed for having a desired maximum steady state variation at the end of a given disturbance. But the number of storage systems that must be installed depends on various factors. So this can be defined by the TSO, or can be asked to various users to install a given power for delivering this service. Another important service that is usually coupled to fast frequency regulation is virtual inertia. So the batteries can be used for providing virtual inertia. But what is the inertia of a system? The inertia is the ability of a rotating machine to oppose variation in speed thanks to the kinetic energy of its rotor. So it's the first and natural response of the generator to a disturbance, and is usually expressed in seconds, and that is the time that machine will stop if it had to constantly deliver the full kinetic energy of the rotor by injecting power equal to its size into the grid. So this is the formula for calculating the inertia of a rotating generator. Due to the decommissioning of various thermal power plants, the inertia of the system, of the whole electrical system worldwide, is reducing in the years. So we need to replace this inertia, and we can do this thanks to storage systems. Why it's important to reduce the inertia? How can you see from this figure, where we have simulated the same system with the inertia of 7 seconds and with an inertia of 0.7 seconds? Well, the system with the inertia of 7 seconds after the disturbance reach a new value of frequency, but with a frequency nadir that is higher than that of the system with 0.7 seconds inertia. Well, the difference in frequency nadir is not is very important, because the frequency nadir can activate the minimum frequency protection relay, and can cause the detachment of the power plant from the system. So if the inertia of the system decreases, we have higher probability that the minimum frequency protections, or that the rock of protection are triggered, detaching the power plants. These are typical inertia value of power plants, and you can see in the tables that wind and photovoltaic plants have inertia that is equal to 0. So the increase of wind and photovoltaic plants is reducing the inertia of the systems. And ENSO-E is indeed suggesting new formulas for calculating system inertia in the presence of renewables. So this on the left is the classical formula that has been used for calculating the system inertia without significant amounts of photovoltaic and wind generation. And the second formula on the right is the new one suggested by Enzo E for calculating system inertia when we have significant contribution from inverter-based generator like type 3 or type 4 wind plants or photovoltaic systems. If we compare the two formulas, they are similar, they are equal in the denominator, but they are different in the denominator, where P load in the second case is used instead of the sum of the rated power of all the generator of the systems. Since this sum is calculated only considering a rotating machine, if we have a large contribution from wind plants and photovoltaics, P loads in the new condition is higher than SN cis. And so we can say that due to the spread of renewables, the inertia of the system is reducing during the year. And so we must contrast this reduction, and we can do it using, for example, battery storage systems for simulating the inertia of a power plant. So in this case, we have a specific control of the VSC converter of the storage system. In this case, we can also use a supercapacitor, for example, not necessarily batteries. And this new control is represented in different ways. You find in this slide two different implementations of the synthetic inertia control that allow the battery storage system to provide not only fast frequency regulation that is activated by frequency differences, but also to provide a virtual inertia to simulate the inertia of a rotating machine activated by the value of the Rokov, so activated by the variation, the derivative of the frequency in time. If the a given dead band of the frequency is not respected, the frequency is derived, and the derivative is multiplied for this gain that represents the virtual inertia of the system, and an amount of power is injected into the system in the very first seconds from the disturbance, simulating the natural response of a thermal or usually of a rotating machine. And so the same system that we examined before, where we have synchronous generator, the natural response of the power system, if we include batteries participating to frequency regulation and providing synthetic or virtual inertia, can be represented in this way. We have here the frequency variation that is sent to the converter to which the battery is interfaced, is connected, and thanks to this gain, a power is injected into the grid proportional to the frequency variation. The same frequency variation is derivated and then multiplied by Ki, and so the same converter that is providing fast frequency regulation provides also virtual inertia, and in this way we can proceed with the decommissioning, for example, of carbon power plants, replacing them with battery storage systems. A few years ago, I participated into the writing of a proposal for a European research project in which we suggest to install battery storage systems in sites where carbon power plants were installed for replacing their contribution to frequency regulation and to the inertia. That was very interesting because in replacing the traditional system with batteries, respecting the same locations, allowed to not modify the grid that was already adequate for carrying the power that should have been delivered by the batteries. Finally, the last function that the last service that the storage system can provide is black start. What is black start? When after a blackout, we need to restore the electrical power grid, and in this case, we need to do it very quickly and minimizing the impact of the blackout. And minimizing the dangerous condition that can rise without electricity, and minimizing also the economic expenses for paying eventual damages to end users. So for restarting the system after the blackout, we typically involve units named black start providers that can include battery storage system, like in this case, the case represented here. These black start providers start up individually isolated power stations and gradually reconnect them to form a larger interconnected grid. In this case, the size of the BESS is chosen to provide the maximum power that the generator that has to be started needs to start, and to provide the energy that is the area of this diagram. You can see that in a first phase, we have to restore energize the transmission line. Then we will connect the black start provider to a transmission line. We will energize the transmission line. Then we close the switch that connected the generator to the line, and we energize the generator. So the generator takes from the storage the energy needed for restarting, and then we have a ramp down of the energy for reducing the load. For doing this, it's important that the VSC converter coupled to the BESS is controlled with the grid forming control. This is only one of the possible implementation of grid forming, but grid forming converters are usually converters that are connected to batteries, but also to wind plants, photovoltaic systems, and can be operated like they were synchronous generators connected to the grid. So they are able to create both voltage and frequency in a grid totally shut down. For providing each service, we can use different technologies. In this figure, you see for each service the battery technology is more suitable. For example, we have a great prevalence of lithium-ion batteries, both alone and coupled with supercapacitor or other kind of batteries. And you see the response time requirements for each service. Frequency regulation normally under 100 milliseconds, voltage support normally under 200 milliseconds, and so on, you see that we have a very different response time for each service. For example, peak shaving or energy arbitrage needs 10 of minutes, black start less than 30 minutes, frequency and voltage regulation less than 1 second, and so on. Load following is considered adequate and competitive if it occurs in less than 5 minutes. And you see also the duration requirements. So frequency regulation from 15 minutes to 1 hour, depending on which level, primary or secondary, voltage support continuously, and so on, and some indication of the possible revenues for these services. Consider that these values are very variable from country to country. Finally, for concluding this part of the lecture, I want to show you what ENTSO-E's position paper on electric storage identifies as a general principle that should guide the future policy and investment framework for storage to be taken up to a European level. Storage activities should be market-based for making their market competitive to other technologies. Storage system operation should not be restricted to a single service. So if we consider to install a storage system for a single service, in general, this won't be economic, won't be profitable. So the same storage should provide more services, and moreover, TSO and DSOs should have access to all data of central distribution storage facility for system security. These are the indications from ENTSO-E. Now, let's examine some case studies. One interesting application of batteries in voltage regulation is those of e-STATCOM. You know that STATCOM are FECs, flexible alternate current transmission system devices that are used for voltage regulation, and the STATCOMs are the more flexible and the more precise and competitive devices that can be used for voltage regulation. Where STATCOM use only a capacitance for regulating the voltage, but if we couple this capacitor to a battery, we can create a device called an enhanced STATCOM or e-STATCOM. This device is, you can see it in this figure. We have capacitors and batteries and the conversion system as disadvantages with respect to the classical STATCOM. It can regulate reactive and active power. The DC side is connected not only to DC capacitor, but also to energy sources of storage like batteries and supercapacitors. While the STATCOM cannot continuously exchange active power, and so it's considered like a passive source, the e-STATCOM can supply absorb active power continuously. And so the applications are different. So the first one, the STATCOM, is used for voltage support, dynamic reactive compensation, while the e-STATCOM is used for power quality improvement, frequency support, and load management. Obviously, the complex and complexity of an e-STATCOM are higher than those of the STATCOM. This was one of the first application that I want to show you, and we can say the e-STATCOM are still in a developing phase, so they are becoming during time a reality for our system, but they are still quite in discussion. Another case study that I want you to present is the Terna Storage Lab, an Italian case study. We have, you know that Terna is the transmission system, the Italian transmission system operator, and Terna few years ago has installed in Sicily and in Sardinia the so-named storage lab. So two different installations where different technologies of batteries, different batteries technologies were tested for providing frequency regulation. So these are power-intensive services provided by these technologies in Sicily and by these technologies in Sardinia. So you can see that the installation comprises power that for each technologies are around 1 megawatts with different charging and discharging times. Well, the interesting results has been obtained testing each technology for primary frequency regulation. So this is the activation curve of the voltage source converter connected to the storage systems, and this was the function that represents this graph, and the storage systems have been tested with two different cycles. So each technology has been tested with a standard charge-discharge cycle that is represented on the left, and then has been tested with the frequency cycle, considering that the state of charge the SOC can vary between 0% and 100% in order to stress in either way the operation of the batteries with that group of 0.075. Well, the interesting results, this is a very interesting results since an experimental results that can tell us a lot of things about the use of these systems for grid service, is that the tests have demonstrated that the frequency regulation cycles aids the batteries much more than the standard cycle. And so we can use batteries for frequency regulation. Frequency regulation is a very important function for security of the system, but remember that the life of batteries can be reduced in a faster way, can be reduced faster than if they are used for other applications like energy arbitrage, load following, or peak shaving. Another application that I show you is the fast reserve. We already talked about fast frequency regulation provided by batteries. This is a real project implemented in Italy. Since in the next year we will dismiss a lot of old power plants, we will lose the inertial response, the regulation response and the inertial response of these plants. So we must replace the inertia of these plants and the fast response in the primary frequency regulation, and we will do it using storage systems that will be installed in various parts of the countries. So there is a plan to install them in Sicily, in Sardinia, and southern Italy and northern Italy. I think that I don't remember, but it should be for Italy almost 250 or 300 megawatts of storage system necessary for this service, for replacing the power plants that will be decommissioned. And the fast reserve is operated in this way. Various units with rated power between 1 megawatts and 25 megawatts will be installed in the country, and they must be able to provide the full power in 1 second, maintain the injection of that power for 30 seconds, and then reduce the power injection into the grid in 300 seconds, in 5 minutes. In this way, they will provide fast frequency regulation and virtual inertia, and they must be able to provide this service 1,000 times in 1 year, and will receive a revenue for the provision of the service. Why they are important? We have simulated the use of fast reserve like a tool that can be implemented in all Europe, in the whole continental Europe synchronous area. And we have calculated that for contrasting the reduction of the frequency, primary frequency regulation reserve of the continental Euro area, and for contrasting the reduction of the virtual inertia of the natural inertia of the continental Europe area from 2020 to 2040, it is necessary to install 4 gigawatts of fast reserve units behaving like the Italian ones, and with a very with a not significant expense for the power systems. If we are able to install 4 gigawatts of fast reserve units in the from now to 2040, the performance of the power system of the continental Europe synchronous area will not vary in a significant way, and the same security that we have now could be maintained in the next 20 years. We have also applied the use of the fast frequency on the fast reserve unit in a real case, the system split that happened on the 8th of January 2021, and we have demonstrated that thanks to the fast reserve units, if they would have been implemented in all Europe, the system split would have not occurred, and the system would be the Europe would be a single area for all time. Another case study, a black start of a power plant in Sicily. Here we have controlled the battery storage system with the grid forming control to energize the line that supply the Termini Imerese power plant. Termini Imerese is an important power plant close to Palermo, and it will be the closest power plant to the new HVDC connection between Sicily and Sardinia, that is the West Tyrrhenian link. Well, the system controlled with the grid forming control, you find all the specific, has been used for a soft black start. So the system is started with a voltage ramp of 500 kilovolt seconds. After 0.7 seconds, the voltage has been established. Then the line that connect the battery to the power plant of Termini Imerese is energized with some oscillation in powers, and then finally the power plant of Termini Imerese is energized and is connected again to the grid. So we have demonstrated the use of the battery storage system for in this case study for black start operation, and we also have analyzed the transient in voltage and currents, and we have found that it can be used efficiently. Since we have a few times here, I want to go faster here. This is another case study. In this case, we are using not stationary storage systems, but traction storage system, traction batteries, the one on board of vehicle-to-grid electric vehicles, that for providing frequency regulation and for contrasting the concerns about user reluctance due to range anxiety and battery degradation, three strategies are proposed for for discharging or charging the batteries of the electric vehicles and reducing the anxiety of their owners. And these three controls of the batteries have been demonstrated to be effective. So we can use also vehicle-to-grid technology, also traction batteries for providing frequency regulation without compromising the battery life of the cars. I want to go to the final part of my presentation. Here we confront some performances of the various batteries technologies from the tables that I showed you before. You have seen that not all technologies are suitable for providing a given service, so we must compare the different technologies for choosing which one is more suitable for each service, and we can do it based on technical and economical performance metrics. The technical performance metrics are usually this one. Once they are energy related, so energy density, round trip efficiency, and capacity retentions. Power related, power density, response time, and current density. Operational, so temperature stability. When the battery provides a service, it must be ensured temperature stability, state estimation accuracy, and cycling stability. And we have seen how Terna have investigated the variation in lifetime of each battery with those experiment done in the two power intensive installation in Sicily and in Sardinia, and then grid integration technical performance metrics that are power quality, frequency regulation, and voltage support. For each metric, you find in this table the typical range and values that you can consider acceptable for the batteries and on the basis of which you can choose a given technology. Regarding the energy and economic performance metrics, we must face the problem of the cost. Capital operating costs that are initial cost and annual operating costs that are quite different for each technology. You can see here that initial capital costs are more expensive, are highest for flow batteries and are the lowest for sodium-based batteries. Annual operating costs are the highest for base operation, and then the personal is the lowest one, are the lowest one. And then we have to calculate the grid service revenue, and here you find some indication for peak shaving service, frequency regulation, and energy arbitrage. But how I said before, these values depends on the specific country, because in many countries some services are totally free and some services are still not paid. And then we have to calculate payback time and other parameters that are market development indicators, the performance risk factors that are technical reliability and market certainty and policy stability, and the economical life cycle metrics. So this must be taken into account for comparing the payback time of the investment with the life of the battery. And you find here that the highest are flow batteries, the lowest economic lifetime metrics here in years are the ones of lithium-ion batteries. Well, I stayed in the time, in the time slot of 2 hours, and I want to conclude with this slide where I'm indicating some future directions that must be taken for making batteries and in general energy storage competitive in the market for the provision of grid services. It is important to perform a field experimentation to test the actual performance and lifetime of different storage systems in different applications. So not only frequency regulation, but also voltage regulation, energy arbitrage, and so on. It's necessary to perform a field experimentation to test the real effectiveness of grid-forming controls of VSC converters connected to storage systems. Indeed, grid-forming controls are still studied from a theoretical point of view, and still few pilot projects have been implemented. I have to say that in the last 2 years, I heard about also new application and some commercial applications. So times are becoming mature for this technology. And then we need to clearly define the remuneration for the different ancillary services in order to favor economic choices regarding the installation of electric storage system instead of traditional grid service technologies for those services. Only in these ways we can hope that investors can spend their money on batteries, on electrical storage systems for this kind of application. Here you find some reference that I used for this presentation, but if you need to know more about this topic, you can contact me. This is my email address, and thanks for your attention.
Yes, maybe we have 3 minutes for question and answers, if anybody has some question. I can see some people typing.
Yes, I can see a colleague typing from the chat.
Yes.
Maybe we have time only for this question.
Yes. Oh, no, just saying thank you.
Thank you for the presentation.
Okay.
Thank you to all the participants. And I think that if you want, I can share also my slides.
Okay, thank you very much for that.
Later. I will send you an email.
Thank you very much. Thank you so. Oh yes, we have one more question.
We have a question. We can try to answer.
Yes.
What do you think about hybrid energy storage systems to improve the lifetime of batteries? Yes, this is a very important question. What I think about hybrid energy storage system. This can be a good solution. For example, for providing service like virtual inertia, could be important to couple supercapacitors with lithium-ion batteries in order to use both technologies together, and using lithium-ion batteries for energy arbitrage or for secondary frequency regulation or for the second part of primary frequency regulation, while supercapacitor can provide the virtual inertial response. And this way we can increase lifespan of lithium-ion batteries. This can be a solution, and this is only one example that you can find. And from an economical point of view, of course, this can be a solution, because the increasing lifespan of lithium-ion can allow us to maintain into service that installation for a longer time. Okay, thank you for the question, and thank you for your participation again. And if you have other curiosities, other questions, please contact me using the email address in the presentation. Thank you. Bye-bye.